Okay, let's talk about the Carnot engine. Once again, we talked about the fact that reversible engines always have a higher efficiency than irreversible engines operating across two heat reservoirs, a hot reservoir and a cold reservoir. Okay. Now, somebody by the name of Nicholas Leonard Carnot, who lived from 1796 to 1832, wanted to work on the efficiency of steam engines. Wanted to find out what is the maximum efficiency that he could achieve. Okay, Carnot was a French-Egyptian physicist, and his work was very, very important to improving the efficiency of engines. Now, a theoretical engine developed by Carnot is not really physically possible, but we can get pretty close. The heat engine operated in an ideal reversible cycle. Again, reversible, we know that's going to achieve the highest efficiency. And we call this the Carnot cycle. Now, Carnot's theorem is no real engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. It's just another version of the Kelvin statement that we saw in the previous section. Okay, so basically, what we can do is we can calculate what is known as the Carnot efficiency. That's an E with a little subscript C, and any engine that we produce, okay, is going to be less efficient than that maximum. So the Carnot efficiency is the upper limit. You can't do better than that, because otherwise you would violate the second law of thermodynamics. So he discovered the if you put four theoretical cycles together, he would get the greatest efficiency. And you got to follow this because this is a little complicated. We have an isothermal expansion from A to B. Then we do an adiabatic expansion from B to C. Then an isothermal compression from C to D. And then an adiabatic compression from D to A. Okay, and it's going around in a clockwise direction as all heat engines do. Okay, so this would be the greatest efficiency that could be achieved. All right, and he was able to figure this out. Now, again, Carnot cycle, we can picture it a number of different ways. Thinking about what's happening with the heat. The first part, we're doing isothermal expansion, and we're adding heat during this expansion. Then part two, there's no heat added. We just allow the gas to adiabatically expand. So the temperature drops. Part three, we take heat out of the system. Okay. And then part four, we're allowing adiabatic compression. So the gas is heating back up, converting converting work into internal energy. And again, this is what it looks like. If you could do it, here would be the isothermal expansion, part A. We'd have it in contact with some energy reservoir at temperature TH. So heat would naturally flow into the gas during the isothermal expansion. Then from B to C, we would have no contact with any reservoir. Then we put in contact with the cold reservoir and allow it to expand. Then compress it. And then again, adiabatic compression. So those would be the four cycles. Okay, what's not so important are each part of the cycle. Okay, those were important for his analysis, what is important for what we need to know is the end result. Again, this is just showing on a PV diagram, QH going in, QC going out, and then the work would be the energy that we could extract from our Carnot engine. So net work is equal to QH minus QC. Okay, that's true for any heat engine. The work is equal to QH minus QC. But this is the result that he got. This is the important thing. And what it says is the maximum efficiency that any heat engine can have is equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. So temperature is in absolute units. It must be in Kelvin. So let's do an analysis here. Let's say that I have a hot reservoir, okay, and I have a cold reservoir. And I'm going to put an engine between the two, okay? Now, the best I can hope for, again, QH is going to flow this way. QC is going to go down here. Work is going to go out here, okay? QH, okay, QC. We won't worry about the actual amount of energy. Let's just worry about the temperature, okay? Let's say that I had my hot reservoir heated up to, what's a good temperature to use? Let's say I have 1,000 degrees. That's a really hot engine, but we'll use 1,000 degrees Kelvin. Let's say that my cold reservoir is operating at 300 degrees. Okay? The best engine with all reversible cycles, the best that I'm going to do for that particular case, EC is going to be equal to 1 minus 300 degrees Kelvin. Divide that by 1,000 degrees Kelvin, okay? 300 divided by 1,000 is going to be 0.3. 1 minus 0.3 is 0.7. So that's a pretty good efficiency. 0.7 is 70% efficient, okay? I'd be happy with that, okay? I get 70 joules out of every 100 joules I put into it. That's perfect, okay? Especially when we consider that the best the human body can do is about 20% efficiency. Now watch what happens when I lower the temperature. The hot reservoir is not going to be as hot, okay? Most cold reservoirs are around 300 degrees Kelvin, so that's a pretty good number to use. But let's say that I operate at a new temperature of 500 degrees Kelvin, okay? What is that going to do to my efficiency? All right, so 300's gone here. This is gone right here. Oh no, 300's still there. Let me just rewrite that. So 300 degrees Kelvin is still my hot reservoir. It looks like an R. Over 500 this time. Okay, so instead of 0.3 now, I have 0.6. Okay, in that second term. So 1 minus 0.6 drops me to 0.4. Now I've dropped, it's only 40% efficiency. So I've decreased the temperature of my hot reservoir here by half. And now I'm down to nearly half the efficiency that I had before. Now, I'm certainly not really happy with that anymore. But again, that would be a perfect engine, okay? That would be a perfectly reversible engine. Real engines are going to be even lower than that, okay? So instead of getting 70% at 1,000 degrees, maybe I only get, I don't know, 60% on a good day. Instead of 40%, maybe I only get 30% for that high temperature of 500, all right? And you can see here why we want to operate these engines at higher and higher temperatures. That TH right there, right? In the denominator, the bigger I make that number, the smaller the second term becomes and the higher my efficiency becomes, okay? So thinking about internal combustion engines, the government has required engines to become more and more efficient. By Carnot's work, how do we make it more efficient? We make them run hotter. Well, that comes at a price, okay? First of all, the metals wear out faster at higher temperatures, so we have to use more expensive alloys. Even the lubricants that we use have to withstand the higher temperatures. So, when you see car manufacturers being required to achieve higher and higher efficiencies using internal combustion engines, it's coming at higher temperatures. That means that engines got to work a lot harder to achieve the same amount of work. Okay, so little thermodynamics there and economics there. So again, a real engine, if we need to calculate the efficiency of the real engine, we need to measure, all right? We need to know what is the work output compared to how much energy from the hot reservoir we put in, okay? The Carnot efficiency says the best you're gonna do is this figure right here. So again, even though we might be able to calculate a Carnot efficiency of, let's say, we'll use the example previously of 70%, real world engines are probably going to be much less than that. Okay, even operating at the same temperatures. Because again, this Carnot cycle, this is saying if we can make everything reversible, that's the best we could do. The real engine, however, okay, has irreversible aspects to it. All right. So two things. One, we try to make the processes as close to reversible as possible, even though we can't do that. And second, we try to make the temperature of the hot reservoir as high as possible. Again, second law of thermodynamics, as we stated before, a heat engine has maximum efficiency if all processes are reversible. That's what Carnot was working on. 2 reversible adiabatic processes and 2 reversible isothermal processes. All heat engines operating between a cold reservoir at temperature Tc and a hot reservoir Th have the same maximum theoretical efficiency because Carnot told us this is the equation, okay? These are the 2 numbers that we're operating between in terms of temperatures, right? No heat engine operating between temperatures of Th and Tc can have a higher efficiency, okay? Efficiency is 0 if there's no difference between the high temperature and the cold temperature because no heat can flow to produce work. And efficiency is 100% if the cold reservoir is at 0 degrees Kelvin, okay? But as we stated before, there's a problem with that. The third law of thermodynamics says, third law says, no, can't do that. Can't do that. Of course, the efficiency increases as Tc goes down, but most of the time, Tc is the cold reservoir. That's just the temperature of the outside. And as Th is raised, we can raise the temperature of the hot reservoir. Okay. But again, in most practical cases, Tc is going to be near room temperature at 300 degrees Kelvin. This always brings up the question, hey, does that mean when it's colder out that the engine is more efficient because we're dumping heat into a colder environment? Well, you might think that that's the case, that lowering TC is going to have that effect. In fact, it doesn't work that way. First of all, it takes longer for the engine to reach its operating temperature. So TH actually stays lower for longer, so there's no offset there. Also, the lubricants become more viscous, which increases the friction, so you don't really gain very much when it's colder outside. Because actually, on a summer day, the temperature is 300 degrees Kelvin. On a cold day, where it's freezing out, what is the temperature like? 270, maybe 250 at the most? That's not going to change that equation by very much. So a cold day doesn't really improve your efficiency very much. Now, the Stirling engine was developed by Robert Stirling in 1816 to improve safety and the efficiency of steam engines. It's based on, well, it says here it's based on the Carnot cycle. It's not exactly based on the Carnot cycle, but it's based on nearly reversible processes to get very, very close to maximum efficiency. One of his designs worked on 2 pistons, and basically one piston would be connected to a hot reservoir, one piston would be connected to a cold reservoir, and the gas would move between the 2 pistons, alternating expansion and compression. Stirling set out to do this because steam engines were blowing up all over the place, and using steam as a working gas was really, really difficult. Okay, well, dangerous. Let's put it that way. It was dangerous. Here with the Stirling engine, the working gas was isolated from the hot and the cold reservoir, so steam explosions were much, much less likely. The problem is a Stirling engine was much bigger and more difficult to produce than a steam engine with the materials available at the time. However, the interesting thing is the Stirling engine is actually coming back. And we're seeing this in solar power. Now, normal photovoltaic cells are around 20% efficient at best. If we use these sun concentrators where the sunlight comes in and is taken in by an absorber connected to a Stirling engine, we can achieve much higher efficiencies, over 50%. Okay. Unfortunately, these types of setups aren't necessarily cheaper to make than photovoltaic cells, but they're more efficient in using the sunlight that's available. So again, real engines compared to the Carnot engines, all real engines are less efficient. You will always be disappointed with the efficiency that you actually get from a real engine compared to what you can compute using Carnot's equation. Okay, this is a pipe dream. That equation right there. Real engines are irreversible because of friction, because of turbulence, because of uneven heating. Okay, and the cycles have to be completed in short amount of time. All right.